Okay, we're showing that we're recording.
That's good.
I am checking audio.
All right.
And we do have that. And now I'm going to turn over control to Mr. Burr.
All right.
And then open up the PowerPoint.
Now, it looks vaguely like slide 58.
Yes. So, Dave, you should be able to do down arrow now. And
all right, let's see if it works. I hit my down arrow. Hitting it again, nothing happened. Uh-oh.
So we experienced this.
You're being stingy. You're not allowing me to control it.
Yeah. I'm just wondering if this is the number of participants, Dave, that because we had this problem last Wednesday, but we had no problem in our test case and our Friday or Sunday sessions. So because we're burning time here, won't we do the own method? And we have some people that are going off of hard copies on this, so let's do the old next screen.
Slide number then. All right, so we're going to be talking about baseline adjustments. This is the second half of the DOTA AMVwebinar, courtesy of DBET. And we covered a lot of ground last time in terms of some of the basics of M&V, finding baselines, understanding savings uncertainty, baseline types. And now we're going to talk a little bit about routine baseline adjustments on slide 58. So when you're evaluating savings, no matter what method of M&V that you're using, whether that's option A, B, C, or D, you still may be required to make an adjustment to the baseline for current conditions. And those adjustments, depending upon the method you're using, for example, if you're using option B and you're looking at the VFDs for ventilation fans, then fan speed matters. So if fan speed is running outside of the programmed parameter speed, which is needed to achieve the savings, but it's actually running faster than that, then if the cause of that is due to not a failure of JCI's design or operation, but due to a DOTA preference for faster speed, a certain amount of savings will be forfeited, and that'll be an adjustment to the savings. Another thing that could cause a baseline adjustment is a scope change, and as we discussed in the first webinar, there was a fairly substantial scope change to the lighting in phase 1 due to some of the lighting not really being capable of being cost-effectively retrofitted at that time. And so a fair amount of lighting was reduced. There were some additional areas that were added to the scope, but net-net, there was probably a reduction in savings due to the reduction in lighting scope. Then you can look at additional equipment loads that have come on that might be affecting the M&V method that you're using, or changes in control set points or schedules. A good example of that would be for the small HVAC renovations. I think initially JCI had put forward some proposed set points, but actually as we were been monitoring them through construction years 1 and 2, those set points are rarely achieved, and so JCI basically has just forfeited the idea of trying to get savings from different set points, because the amount of savings is actually quite small to begin with. And so I don't think you're even bothering to take an adjustment. You just basically said, well, we're not going to count savings from set point management for these very small HVAC systems because it's not really worth it. But in order to verify the guarantee, when you're going through and doing the M&V process, you do have to look at whatever savings adjustments are made. And if you've read the JCI M&V reports, whether that was for construction year 1 or construction year 2, or even year 2.5, in every case, there will be a discussion of any savings adjustments that were made to account for the impacts of those changes and how that might have affected the savings guarantee calculation. So let's go to slide 59. And I already talked about the top two of these, anticipating what I was going to say. One we didn't mention is that the dedicated control system for lighting had some issues in a few locations, and because of that, JCI was not able to count savings because being unable to control the lighting to deliver the desired schedule for illumination, they actually, I think if I recall right, Larry, they just overrode the controls because they weren't working properly, and they had to forfeit the savings, at least temporarily, until they could get those lighting controls back under control. Is that accurate?
Yes, that is.
Yeah. And probably one of the more significant savings adjustment was the whole discovery that chilled water piping pressure prevented optimization of the chillers because you couldn't really have a completely interconnected system until that got dealt with, and that's part of a fairly sizable construction that's going on right now to make that happen, so that ultimately you can run more sophisticated optimization strategies for the set of chillers.
The add on to that, Dave, is that we're about a month away from completing that work. The cutovers.
I thought it was going to be the end of June or something like that.
Yes.
Yeah, so you're getting close to be able to have a fully functioning interconnected group of chillers, right?
Correct.
Yeah, very good. Well, let's go on to the next slide, which will be 60. So here's these are not necessarily directly relevant, all of these, to this particular project, although one of them is, and that is, these are more non-routine adjustments that you might have to make when calculating savings. And that would be, if someone comes in and replaces the utility meter, a great example of that is a water meter. Water meters are notorious for failing by running slow. And when the water utility comes in and changes out and puts a new water meter in, a lot of times people start looking at their water bills and suddenly their consumption seems to be way up. Well, it's not really that their consumption went up, it's just that now they have an accurate meter, and before they had a slow running meter. So it's important to know when something like that happens at your facility, because that could account for an increase in your utility bill and utility apparent consumption. But there's also can be things like service outages from power quality impacts on equipment operation. And I guess you can tell me, Jeff, is ECO improving their regulation of power quality, or do you still have some significant dirty power incidents?
Yeah, there's still some issues. Benton knows more about that than me.
Yeah. And that can affect certain sensitive equipment, definitely. In this one, probably one of the more significant non-routine adjustments, at least in the early construction years of the project, was one JCI had hoped to get the PV systems up and functioning and the interconnects approved by the utilities. And there were some significant delays on the part of the utilities in approving the interconnection of the PV systems, and that caused JCI to lose the ability to count a fair amount of savings from those PV systems, at least in the early years. Now they're all functional and all connected, but there was a period of time when they were ready on the JCI airport side, but you couldn't get the interconnect stuff finished off with the local utilities, ECO, and I guess some on the Big Island too, right?
Yes, Hilo was problematic too.
Yeah. All right, if we can go to the next slide, 61. So, talking about the adjusting the baseline, you have to realize baselines are not an absolute constant. Rather, they're a level of consumption of utilities and a level of service, whether that's a cooling level or a light level like foot candles, but they're actually based on measurements at a point in time or technical estimates at a specific point in time, and that's what defines the baseline. So then you have to think about a baseline as it's a point of comparison, but changes and impact what happens in the future going forward, because there are variables that can influence that baseline. And we already touched on a few of these, but a couple more would be weather and occupancy. And for example, when we did some utility bill comparisons to cross-check the option A and B methods that JCI was using and compared 2011 to 2015, we found out that occupancy at OGG had gone up about 20%. So, that's great, for tourism and for DOTA, but it did put an additional load on the chiller system. And that would be an example where you had to take that into account if you wanted to use a cross-check of an option C method where you did some utility bill analysis against options A and B. And when you do that, and this is the sort of the ironic part, whenever you do an option C type of approach where you try to use utility bill data, you actually never can just use utility bill data. You have to run around and look at all the impacts on that meter, all the additional loads that could have influenced what that utility meter is reading, and that means you're going to get into a lot of option A or B or D methods to either simulate and calculate and estimate the effects of various impacts on the meter, and those will have to be deducted in order to make a normalized comparison between the original baseline conditions, what was going on at the point in time in 2011 versus what was going on in 2015. Okay, let's go to the next slide, 62. So here are some savings issues that occurred with the DOTA project. There were some failed VAV boxes at H&L and some deficient air handlers at OGG. So even though, these things were outside the scope of the original JCI project, so even though JCI might be making chilled water with a higher degree of efficiency and delivering it to a terminal air handler unit, that air handler unit was deficient and couldn't deliver the level of service that you really wanted. And so that caused there to be some additions to the scope to repair things that were not included in the original scope. But in order to really truly achieve all the savings, some of the existing equipment inventory actually needs to be upgraded in some respects in order to address that. And this resulted in, since these items weren't part of the original scope, they weren't really JCI's responsibility. And hence the guaranteed savings were achieved by JCI, but the actual savings that were actually delivered at the site were a little bit less because of the fact that there were some deficiencies in existing equipment that wasn't really affected by the original JCI project scope. We could go to the next slide, 63 rather. I want to give you a sort of a conceptual thing. Whenever you use utility meters or even a dedicated sub-meter that measures power, this is a way of thinking about measurement that is conceptually sort of useful. A watt meter, which measures kilowatt hour, actually measures energy, and it can be calibrated. You can check the accuracy of the hardware of the meter, make sure it's working right, and you can test the accuracy of the meter. So that's why we love meters. You can test it for accuracy. But no matter what you do with a kilowatt hour meter, when you start looking into the future and you're talking about avoided utility consumption, you cannot directly measure avoided utility consumption. All you can do is look at what's going on the kilowatt hour meter. What you really need is a what would have happened meter, which predicts the future consumption if there was no EPC project given the future conditions. And you would have to calculate that based on field data and because you actually did a project. So you don't have what would have happened if you hadn't done a project. You have to basically extrapolate and see what would have happened if we did no project. What would the utility consumption be? Well, that would depend on the loads on the facilities and the set points and the schedules and the operation and maintenance and a bunch of other variables. We can go to the next slide. I'll show you this visually on 64. This is what shows you, if you look at the consumption of energy, the kilowatt hour meter is sort of measuring on the left-hand side of those vertical lines, and you're seeing, okay, here's the baseline period, consumption goes up and down between 500 and, almost 1 million kilowatt hours. But here we go month by month over time. And then we go into a construction period between the two vertical lines. And so, the meter shows the consumption is going down. But then we go forward into the performance period, and here you see, yes, it's obviously, just look at the kilowatt hour meter, it's showing that the consumption is reduced, but what you really don't know is the what would have happened meter, and that's what's shown by the red line. If you had done no project, this is most likely what would have happened. And the savings is really the area between the lines. That's the avoided utility consumption. And that's sort of the goal of the M&V process, what you're trying to get a hold of or what you're trying to determine. What utility consumption have we actually avoided with this project? And that's what all our methods, whether they involve meters or short-term measurements or engineering equations or trend log data or any other method we're using to analyze and estimate avoided consumption, that's what we're looking for. So let's go to slide 65. Now, one question that comes up, and there's not a lot of necessarily stipulation in this project, but in some cases, people ask, well, why don't we just measure everything? Well, sometimes the reality is that measurement and verification costs money. And if money was not an issue, you would have no need to consider taking a stipulated assumption, engineering assumption, and using it. But because you can't economically or cost effectively measure everything, you have to consider other factors when you're trying to manage savings uncertainty, which is the axis on the bottom here. Well, one thing you want to know is how large are the estimated savings? First of all, if the savings are fairly certain, in other words, the uncertainty is not high, and the savings are very small, then it's very cost effective often to stipulate the savings, because you can't afford to spend much money on measuring because they're not worth that much, and honestly, they're not that uncertain. You don't have to worry about them that much. When the savings uncertainty is high, but the savings are small, if you go a little bit to the right on the bottom there, well, then you need to consider other factors. Yeah, the savings are uncertain, but the savings are still pretty small. Maybe there's a value in doing some amount of M&V, and then you have to determine how much is reasonable. By the same token, if you go up, sort of look at the left half of the graph, and you look at the vertical side, well, what about when the uncertainty is fairly low, but the savings value is fairly high? Well, the dollars at stake are high. Then you might want to take some measurements, but you may not want to take as many measurements or for as long a time period because the savings are fairly certain. And then you get out into that box which says don't stipulate. That means the savings are very uncertain and the savings are very valuable. You definitely don't want to stipulate. You want to do as much cost-effective measurement as is reasonable. And this is just, once again, conceptually thinking about the trade-off between risk and accuracy. We can go to slide 66. So, when's it appropriate to use stipulations? When a usage factor is well documented. Here's an example. If you want to look at hours of lighting as a usage factor, you might go out and you might have put in some short-term sensors to track, or you might have done visual inspections of the property, and you've pretty well established what the lighting run hours are. Well, then it's appropriate to use a stipulation because you don't. It's not necessarily going to be dramatically changing. Also, if you have a high probability of savings performance, well, when you put in a more efficient light fixture, you have a pretty high likelihood of saving energy, when you go from one that's much more efficient. But that's just a simple example. Let's go to slide 67. So the other time we talked about when stipulations are more appropriate using engineering estimates or is when the savings are very small, when the M&V is not cost effective, when you're not getting any other value out of the M&V data, and your stipulation is based on defensible engineering assumptions. Those are all times when you could use stipulated values. Let's go to 68. So some inappropriate uses of stipulations are when the project savings are really large, or the performance of the ECM is very complicated, or key variables are not stable, like the runtime on a fan, or it shifts a lot of performance risk to the customer that the customer is not able to readily manage, or if the customer simply doesn't understand the project commitment to that stipulation and what it implies economically, and or they're averse to taking the risk of using a particular engineering estimate. Those are cases where you would not want to use stipulation. Let's go to 69. So I want to talk a little bit about the International Performance Measurement and Verification Protocol. It was begun by the U.S. Department of Energy in 1994, and it was published in 96, and expanded and revised in 97, and now they come out with a new version every 2, 3, 4 years. Actually sat on the indoor environmental appendix of the IPMVP when it was first being drafted. I was a representative on that committee many, many years ago. But the bottom line is they just keep refining it. Now, one thing to understand about IPMVP, it's not a standard as much as it is a recipe book. It says, here are all the questions and considerations you need to think about when you're defining an M&V plan, and here's what good practice is, and here's what a lot of guidelines are. But it still has to be adapted to your specific situation, and you have to make judgments, expert judgments on what's the most appropriate approach from an economic and from a technical accuracy point of view in your situation. Let's go to the next slide, which is 70.
Hold on.
Sure.
All right. Okay, I am stuck up in
Water
that.
P has control now.
Yeah.
Get him to try.
All right. I tried hiding the banner on top there, Dave, and so
It just works now, Larry. It went to 70.
yeah.
So if you're interested in really getting into some detailed research, you can go to these websites. Now, IPMVP is administered by the Efficiency Evaluation Organization, and there's their website up there. Or if you want to see what ASHRAE has done in extending their guidance for M&V and ASHRAE Guideline 14, it only covers options B, C, and D in more technical detail. But if you really want to get into the weeds on this, you can have a lot of fun reading about that stuff. So let's go to slide 71. So just thinking about option A, there's typically some stipulated usage factors, but there's always some measured key parameter. Otherwise, it wouldn't be option A if you didn't measure something. And typically, a good example here is lighting, where you measure KW before and after change out lighting fixtures. And that would be an example of the key parameter that you're measuring. And the stipulated usage factor would be typically runtime or run hours. In option B, there's usually some sort of metered consumption or production performance. A good example here is the output from the PV systems, where you actually have a dedicated PV meter, so you can measure the production and then you can normalize it based on solar irradiance, etc. But there you have a more dedicated look at what's going on. And there are other ways you can do option B too, which we'll talk about a little later. But option C is what most people in the finance world think about when they think about, oh, I'm going to save money on my utility bill. They assume you're going to use a utility meter and that'll solve it. That'll give us everything we need to know. But as you'll see later, it's not really true. It'll give part of what you need to know, but there's a lot of other data you're going to have to collect and analyze before you can distinguish the signal from the noise in the utility bill analysis. And then lastly, option D, which was used a fair amount on this project for estimating savings, although it's not really being used particularly in the ongoing M&V. But this is where you look at a building model and you calculate, based on inputs into the model, what the savings would be. We talked about this a little earlier when we discussed the eQuest model. And you actually are able to determine by sort of tinkering with the inputs of the model how the savings are influenced from specific ECMs. And the nice thing is it takes account of the interactions between various ECMs. So if we could go to slide 72. Now, what factors affect what M&V method you want to use? Well, how many ECMs do you have to deal with? That's a factor. How complicated are they? How large are the savings? The larger the savings, the more it may be worthwhile investing money in M&V to track them. How uncertain the savings are, which we talked about when they had that little graph on stipulation. And what's the risk allocation for savings if there's a shortfall? In this case, I think about 90% of HVAC savings are guaranteed compared to what was projected in the IGA, and about 95% of the lighting savings are guaranteed compared to what was projected in the investment grade audit. So therefore, there is a safety margin. And you're looking at, well, if there's a small shortfall compared to what the IGA said, you're still going to make your guarantee without a problem. But I know if you look at a really large data set, I was actually on a phone call earlier this morning with Lawrence Berkeley National Labs, where they looked at over 6,000 projects that they have in their database. And there, I think, because a lot of those are older projects where people were even more conservative in providing that safety margin, they came in around 85% of savings that were projected were typically guaranteed. Now, in more recent years, people have whittled that safety margin down a little bit, closer to the 5 to 10% instead of a 15% safety margin. Frankly, since they have more experience and better results, and they are usually overachieving their guarantees anyway. Another factor that is relevant for this project, we'll talk more about it later, is the availability and capability of an EMS system to help support the M&V function. You could go to slide 73. So in option A, you have defined baseline conditions, and you may be doing some spot measurements. If you look at the last bullet there, short-term measured data to estimate the performance factor, the key parameter, which in this case is KW. Usage factor is runtime hours, how much is that lighting on? And over time, you may be doing what's called, physical monitoring, just doing visual inspection of the equipment to make sure it's still in place. Let me give you an example from another project I worked on. I did a big university project in southern Illinois, many years ago, and we went back and we did pre and post measurements on the lighting, and then when we went back and did annual visual walkthrough and inspected a big sample of the lighting, we found actually on the order of between 5 and 10% of the fixtures had some kind of issue, some kind of error, or something had changed. There was some requirement to check it out and make some minor adjustment or minor repair or adjustment. So, that can be like, I'll call it a supplement to option A, where you're effectively sort of checking, the equipment works when we put it in, now we're just monitoring it to make sure things are still working. Go to slide 74. So with option A, you're typically doing a one-time post-measurement after you've done a pre-measurement. This was also done on a transformer replacement, where effectively one-time sort of pre and post. And for small HVAC replacement, essentially there you're just using the efficiency of the new equipment, and you're looking at a calculation based on the pre and post equipment efficiency, because the savings are quite small from the small HVAC equipment. That's not true of lighting or so much the transformer replacement. There the savings are larger, but they're fairly certain also. Then there's option A with annual measurements. Well, the HVAC associated with the chill water system, there's some annual measurements going on of that HVAC to make sure it's functioning, and of the chilled water system itself. There are annual measurements being taken to monitor the kW per ton of the chiller systems. Let's go to slide 75. So in option B, you're looking at verifying energy and cost data obtained over the term of the agreement, and you're doing some form of long-term monitoring. Whether you're continuously measuring or periodically measuring, you're tracking certain operational factors. It could be kWh, it could be kW per ton, it could be the band speed, which is more probable in this case, or the hertz that controls the fan speed, which is even more probable in this case. And it's typically performed at the equipment or system level and goes on for the term of the project. A good example here is the VFD for ventilation fans. But the nice thing is, it gives you a longer-term picture of the performance of savings. Let's go to slide 75, or actually 76, actually. Where did DOT use the M&V option B? Well, with your trend log post-measurement on the ventilation fans, but also the PV system normalized for production factors like solar irradiance. So those are a couple examples. Go to slide 77. Now, what sort of issues did DOTA have? These are just some examples. On the ventilation fans, using the VFD really to control the fan speed to maintain air quality, to get rid of vehicle exhaust, to avoid essentially carbon monoxide and NOx. The whole strategy for this particular ECM is a reduction in massive excess ventilation, because these fans are actually located outside. So effectively, they're in an area that is not nominally, it's not actually it's not a cooled area by artificial cooling. It's simply cooled by, these fans being used to ventilate, to protect air quality. The nice thing about this measure is there's really large energy and demand savings, but they're critically dependent on fan speed. And at least in the early stages of this project, there were a lot of manual overrides of the fan speeds, which significantly reduced the amount of savings that could be achieved. So let's go to slide 78. So why were the fans being overridden? Well, because actually, if you run the fan at a higher speed, you're going to get a cooling effect from ventilation effectiveness. And if you're outside working and you want to be a little cooler, that was a way to feel a little more comfortable, a little cooler. But it comes at a very high energy cost. So the trend log data that's being used to control fan speed is really the hertz on the VFD. It's used as an indicator of the fan speed to monitor savings. And that's sort of where JCI ended up in terms of the tracking, what data they're going to actually trend log. Prior to the electronic control system for the VFDs on ventilation fans, they were using field inspections to identify manual overrides of the fan speed. Let's go to slide 79 rather. So what is option C, which is not really being used on this project, but in this case, you're looking at the whole building level, where you're looking at all the utility meters that serve that particular building or facility. And in the case of DOTA, if you were really using option C here, you would have well over 100 meters to be looking at, because there's lots of utility meters in different locations. And in that, but it's not just looking at the utility bill. You also have to analyze all the other variables that can impact those meter readings. So when you're trying to sort out the changes due to specific end-use loads on the same meter, it can be complicated, and it requires you to do lots of option A type calculations or measurements to make adjustments to the quote-unquote utility bill baseline. And, we had an example of that when we compared 2011 to 2015 for year 2 of the construction year. Next slide, which is 80. Option D is using a model like eQuest to determine savings through simulating a whole building or a system within a building. And you calibrate it with utility data so that you show, hey, my model, if I take all the input variables that describe this building or facility, and I put those variables in, and then I compare that to the historical utility consumption, this model accurately predicts the historical utility consumption. Therefore, I can use it to predict future utility consumption if we change some of these variables over time going forward due to ECMs that are put in or changes in operating schedules. And it's used most commonly for more complex building systems. And it was used model savings for a substantial percentage of the savings on this project, although not the majority, but a substantial amount. I think about maybe about 36%. I have to flip back to that old slide, but roughly that.
Yes, and Dave, if I could add one more point on this, we're only also using the modeling to measure the synergies between ECMs. So in your previous session, you talked about the lighting retrofit and the reduction on the cooling load.
Yeah, interactive effects.
Right.
That's right. Because option D gives you a way to capture that. That is a little more sophisticated than most of the other methods. Don't necessarily allow you to easily capture. Well, option C sort of does, but option D is in some ways a cleaner way to look for interactive effects. We could go to slide 81. Here you can see relative cost versus accuracy of the different methods, and to some extent, this shows you if you use option A, it should be accurate to plus or minus 20%. It sometimes can be better than that, depending on how large a sample you're taking. Option B, 10 to 20%. Option C, 20%. Option D potentially gives you probably the lowest errors if you have a really good model, but medium in cost, option B, medium in cost. And the funny thing is, people say, well, why do you say option C is the highest cost? Because a lot of people think option C is going to be the lowest cost, and actually option A turns out to typically be the lowest cost method of doing M&V. The reason why option C is the highest cost is because people make so many changes in their dynamic facilities that to track them all down takes hundreds and hundreds of hours of engineering time. I'll just give you an example. I did a project which was much smaller and less complicated than the one you're doing. And in 1 year, the owner of that project made almost 30 material changes that were not part of the project's original scope that had major impacts on ECMs. Well, when you realize, engineering time spent to track down the impacts of all those changes and all the data you had to collect and analyze and track, option C gets to be, or can be, a very expensive method. And that's why, I'm going to give you a little side note here. It's not in your slide, but in all the federal projects that are done by the federal government, which is billions of EPC projects, 61% of all the projects use option A, by far and away the most common method of M&V. Option B is used 17% of the time. Option D, the simulation type, is used 14% of the time, and option C is only used 8% of the time. Well, there's a reason for that. It really is as expensive as I said it was in practice. So it turns out it's not really more accurate than option A, but it can be a lot more expensive. Hence, option A gets used about, way more often. So let's go to slide 82. Here you can this is just an example of savings calculation technical details. I'm not going to go real deep into this, but just to give you an idea of some of the subtleties of M&V. When you have to adjust for the actual motor load factor. Like if you assume that the load on a motor, when you're calculating savings from that motor is loaded to, let's say, 80%, but it's really only loaded to 65%, well, then when you do the savings calculation, you're going to be wrong about the savings because you used the wrong motor load when you looked at the savings. You basically used an incorrect load factor when you did your assumption for the baseline. Another possibility, this is one of my favorite little stories. The largest utility in the state of Illinois, ComEd, decided they were going to replace like 10 100 horsepower high efficiency motors that was in one of their high-rise towers. And they put meters on it, and they went in and they put in these 10 high efficiency motors. They started checking the meters, and they weren't getting any significant savings, and they couldn't figure out what was wrong. Well, the mistake they made was they didn't check the motor RPM, the rotations per minute, versus the new. And it turns out that work equals force times distance. And if you run a motor at a much faster speed, yeah, you do more work, but it's sort of like unnecessary work, and you use energy that you hadn't planned to use because your RPMs are too fast. You want to match the RPMs of the old motor and the new motor so that you don't do a lot of unnecessary work that burns up energy. Even though you're doing it efficiently, you're doing excess work, and therefore you're not saving the energy you thought you were going to save. This is sort of a subtle point, and not necessarily here. If I recall, Larry, except for maybe the small HVAC stuff that you changed out and the chillers that you changed out, you didn't do a lot of motor replacements on the fans, did you?
We actually did at H&L, Dave, primarily so that we ensured that we had induction rated motors for use with VFDs.
Right, so you had to replace motors to make sure they would work. And I'm assuming when you did that, you tried to match the RPMs of the old versus the new.
Yes.
Yeah, but that's sort of an important factor. Another thing that can happen when you get down into the weeds and the details is the power factor can degrade. And kW savings with a kVA increase. So, you can get in and you can look at things like, haven't looked at ECO's rate structure recently enough to remember. Do they have a power factor penalty if you fall too low?
Yes.
Yeah, then that's something you have to sometimes pay attention to. But these are like the subtleties that you get into when you start to get into the really detailed characteristics of the equipment and how it performs over time. So let's go to slide 83. Here's another example which is relevant to what was done here, because not only did you put in much more efficient lighting, you also controlled it better so that in cases where you didn't need it to be on, you could shut it off, or in places where you could reduce the lumen level, you did that. So there were chances here, you could see the lighting curve pre-ECM and then the lighting curve post-ECM, and obviously the delta in between those two lines, pre-ECM and post-ECM, is the avoided utility consumption. Let's go to slide 84. So to achieve high performance, what do you need to maintain it over time? Well, you need reliable monitored data, which JCI will be getting from both things like their dedicated metering for the PV system and also the EMS system, the trend log data. You have to understand the data that you receive and have the active cooperation of site operators so they can take an appropriate response to what the data tells them about what's happening to savings, whether you're meeting the targets or not, or whether you're veering off of what your trend log program goal is. You want to operate the facilities according to the original design intent in order to achieve the savings. This is aided by having easy to understand graphic formats and doing a certain amount of monitoring-based commissioning of the systems, especially large energy-consuming systems like the chiller system. And maybe talk a little bit more about that later. But the whole idea here is to have feedback on what's going on so that you can chase the feedback loop, you can close it, and improve performance iteratively over time. As you get more information, you learn what's happening, and then your energy manager can focus on the performance analytics and make sure it's actually functioning. Jeff, do you have someone designated now at DOTA who's effectively your energy manager?
Yeah, Evan and Benton.
Evan and Benton are. And I know ultimately I saw that JCI, at least as time comes on, maybe when the chiller optimization thing is, that they'll have someone who's going to be involved in that role. I don't know if the exact term is energy manager, but I'll call it chiller optimization manager, Eddie Klaus, right?
Yes, that's correct.
Yeah. So let's go to slide 85. So when you want to maintain high performance over time, you need to focus on the results, which is link the data you're collecting and analyzing to the results you're trying to achieve. And what helps with an energy management system is it helps you develop a deeper understanding of how your building is operating and what affects the performance of your building systems by giving you a data window into how your equipment is performing. It allows you to have better control and understanding. And the nice thing is you keep learning as you go along and figuring out strategies that maybe improve equipment operation, improve comfort, improve savings. But in order for that to happen, you have to have relatively rapid and frequent feedback on the performance of your energy-using systems. And then commissioning can be brought in as well to tune over time. This is important because the monitoring data can be used to tune the performance of your equipment. Let's go to slide 86. So what are some of the sources of monitoring data that you might be looking at? Well, you could look at a utility bill. You could look at utility meter readings. For example, on the PV system, that would be a case there where you're looking at an output meter. You can look at weather data. In this case, once again, PV is a good example. You have to look at solar irradiation data. You could look at a building operation and maintenance log to see what's going on with the level of O&M on critical equipment. You could look at whoever keeps track of building equipment changes, what has happened in the building that has altered the configuration of equipment, whether there's been a failure or a repair or something else. And you can look at trend log data that's coming off the energy management system, that BAS trend data, and see how the trend data that you're analyzing, what it's telling you about what's going on with your energy using systems. Go to slide 87. So when you're monitoring energy savings performance, one thing that's key is you need to train whoever's going to respond to that data to be able to interpret the data collected. And Larry, I'm not certain about this. Where are you in the training implementation aspect of things? Have you provided periodic training, or is that in the future?
We're probably somewhere in the middle there, Dave, quite factually, that when it comes to training, we could always use more training. So we have provided training, but with change in personnel and some timers conditions, training is always a constant need.
Is that part of your M&V budget, or is that a separate line item in the contract?
It's in the M&V budget. It hasn't been broken out as a provision of what we got to do, and it's just a recognized need.
Okay. And are you able to provide monitoring data in easy to understand graphic formats off your trend logs?
We're getting there. We're learning ourselves along this, and quite frankly, the dashboards and that are improving.
Good.
So we are at a point where we're close to being ready to present that to DOT for DOT use.
Good. And, I'm assuming when you're using a dashboard, you're comparing with some particular performance target. And the nice thing about a dashboard, it is able to show you, hey, I'm on my target or I'm not on my target.
That's correct. We actually have implemented rule-based analysis of the data against the benchmark and set points, so that we can identify systems that are performing and not performing.
Good. Let's go to slide 88. So another thing that's nice about monitoring is it provides you an incentive for optimizing O&M and documenting the system's performance results. Because if everyone is paying attention, if the ESCO is paying attention and DOTA staff are paying attention, then they tend to be more careful about tracking what's going on with performance. If there's not adequate staff or there's not adequate time to analyze and respond to the data, then system performance can drift. The thing about having timely, relevant, focused feedback on how your system is performing, you can more quickly identify and correct problems. I know that the goal is to get to a point where you can actually use the EMS system for a certain amount of fault detection and diagnostics. When something's not working right, you might be able to determine it from some of the data you're getting back from the EMS. So let's go to slide 89. So when you're documenting what you've monitored, you want to report back the data in units and in dollars or percentages of target savings in a way that makes sense. Some of this would occur actually in a formal written M&V report, but it may also be generated as part of the electronic data from the energy management system. But one of the key things to focus on is variances from predicted savings performance. When you are varying, you want to understand why you're varying from performance and what steps can be taken to bring yourself back on target. Go to slide 90. So what's really important with EMS system, when that's an integral part of your monitoring strategy, is that you maintain it and support it so that you don't get buried in what I call nuisance alarms, and that the sequence of operations is maintained to achieve the optimization of savings over time. Having the data window of an EMS system to look at your building equipment gives you a lot of advantages, but it's dependent upon having quality sensors, making sure that those sensors are cleaned and inspected, and that the equipment they're controlling is functional, for example, dampers or a VAV box. So it's like all these things are linked together, and if you have to sort of maintain the integration of the control sequence of operations to make sure it's actually happening, or you start seeing erosion or degradation of savings. So let's go to slide 91. So what level of monitoring you're doing depends upon what your objectives are. If you're really trying to spot operational problems with equipment, then you might get down to really, daily or hourly consumption pattern monitoring, or even 15-minute interval data, depending upon what the system is. You might also need that monitoring data to calculate a baseline adjustment. I think a good example there is the ventilation fans. In order for JCI to calculate their savings adjustment for that particular ECM, they actually needed to have data, monitoring data, from the EMS system to see what speed the target speed was, what speed they actually ran, what speed they were designed for, and figure out what was going on. Okay, let's go to slide 92. So the nice thing is there are some new monitoring and control technologies coming out, wireless controls. Now, refresh my memory, are the lighting controls a variety of wireless? I'm pretty sure they are.
A variety of
wireless. Your lighting controls are wireless lighting controls.
the Lutron, yes.
Is that accurate?
Yes.
Yeah, that's what I would recall. And then you've got what we were just talking about, the energy information systems or dashboard approach, and even more sophisticated trend logging capability. The nice thing is the cost of these things is falling and they're becoming more common. So let's go to slide 93. So, some lessons learned from working with energy management systems. Sometimes the sensors from EMS systems go bad. That can be due to a failure of the sensor, or just lack of calibration, or a poor location. And I know one example that we had already on this project when we were doing some of the construction period commissioning was some of the air quality sensors had some issues. And I think you had to either replace or repair or recalibrate some of them. Is that correct?
That's correct.
Yeah. So since the sensor is going to ultimately give you a control signal that tells you something about how fast to run a fan, that's something that's important to have as accurate. The nice thing is the more high quality the sensors are, the more they function reliably, and you can have lower life cycle costs. One thing I would say about this is that, sort of reinforcing this point of all things have to sort of work together in a chain of command. The endpoint devices gather data, which is transported, stored, and reported, but ultimately humans have to take appropriate action. Otherwise, the data has limited value. Go to slide 94.
Yeah, Dave, if I could inject and give an example of this, is that we actually had a situation with the Wiki lounge on Inter Island Terminal, 3rd floor, where our system was showing that we were losing the fan systems and the ability to control space temperature every afternoon from about 1 o'clock to 5 o'clock. And it was little bit perplexing in terms of why the space temperature was just going out of bounds and we were not able to maintain space temperature. The human interaction where the brain trust is all of our systems or our logics was indicating we had a problem. But the real solution is that the space sensor was located on a wall that was in the afternoon sunshine.
Yeah, that's one of the oldest tricks in the book. It got exposed to direct radiant heat gain.
We have that in the gates as well.
Yeah, these are some other challenges with direct digital control energy management systems. You know, sometimes, and I'm speaking here more generically, but these are issues to be, you know, if you think generically about potential challenges, sometimes the fees for system design are not as high as they could be, and so the system is under-designed. Or sometimes the controls manufacturers haven't provided enough training or documentation, and therefore the use of the equipment, the potential isn't realized. Or sometimes at the equipment level, protocols are not standardized, and that can create confusion in naming and indexing conventions. Or sometimes if you have to integrate a legacy system, which I guess that's the challenge you didn't really have to face here because you went to new upgraded Medicine system, and really there's not much besides JCI in the way of controls in airport buildings, are there?
Yeah, limited gateways. The train chillers
So with the
were an
train
element.
equipment,
Yeah.
you want some gateways. Have you found that integrating that train equipment into the JCI Medicine system has been fairly straightforward, or do you run into gateway issues?
It was relatively straightforward in this project, and I only say that because the equipment was relatively new. Where this
And
becomes
so
a
you
problem
were in
is when you're
more compatible.
Yeah, the OGG doesn't have it.
right, when you're trying to address a system that's 15, 20 years old, it becomes much more problematic.
Oh yeah, absolutely. Another issue that can come up is if the sequence of operations are pointless or underspecified or altered during implementation and not well documented, and then you run into, you know, you start troubleshooting and you find out, whoops, what's going on, and you have to start doing detective work to figure out what happened. But what, in my experience, one of the things that really makes EDC energy management control systems work properly is having really good training, really good support from the manufacturer of the control system, good naming conventions, and doing a good job of integrating it with the field equipment. And if all those things work right, then you get a much more valuable system for control and optimization. Go to slide 95. So why do monitoring-based commissioning? Well, it promotes sustainability of performance. It can create recurring cost savings, and it strengthens your operational understanding of how the building functions. And it can even justify additional funding if you find out, wow, if we could tune this a little bit better, make a slight investment in improved controller equipment, we could actually create some additional savings. And it mitigates the risk of performance, you know, by watching how things go over time. Monitoring-based commissioning allows you to take your performance data and direct your efforts at tuning the system. And, you know, especially, you know, this is less true on Hawaii, but it's not completely untrue. You guys are famous for having the world's best weather, but you do have seasons where there is slight variation in things like the level of rainfall, right? At least that's been my experience, that rain can vary during different periods of the year, and that may require you to do at least some modest amount of seasonal tuning of your chillers, because of the loads they face may be different. I mean, it's pretty steady. I mean, I guess you could answer, given the number of chiller systems you're working with there, but how much overall variation do the chillers actually face on an annual basis?
I'm going to take a guess at this that the variability in the chiller load is on the order of 10 to 15% month to month.
Okay. Yeah, well, that's not trivial. It's not huge, but it's not trivial.
Correct.
Summertime, we're gonna be more efficient, since
Yeah.
our base load is higher in the evening.
Yes, and so the one component is everybody tends to think about dry bulb temperature, where it is really the humidity levels and.
That was my point about the range. It's that latent load that's really probably a bigger variable.
Correct.
All right, let's go to 96. So these are just some things to think about when you're thinking about project performance factors for an EMS. Does the integration logic of the software layer in the control system sequence of operations work properly? Does the operational control spec include ventilation, comfort, hardware points, control strategies, acceptance testing, all these sort of good things that you look for to make sure that your system is providing effective and reliable control. Why do you want to do all these things when you're building out the project? Because you want to make sure it works and functions the way you intend it to work. Let's go to 97. So most EDC systems do not operate as designed. Now, this is improving as we get, all the control systems are getting better and better, but these are some issues that can occur that interfere with their optimal performance. If you don't do enough commissioning, the startup documentation is lacking. If you don't do some long-term tuning, if your sensor quality is not what it should be, if you don't load or write the program properly, if you don't optimize for efficiency, or if you get a bad sensor location, all these things can mess with the quality of your energy management system. So just some things to think about. Go to slide 98. Here's a global view of factors that affect the performance of all your energy saving systems. One is the quality of design of mechanical and electrical equipment. Obviously, the better that is, the better performance you'll get. Electronic controls, how well they work. If these are field controls, like some of the dedicated lighting controls, are they functioning properly? Building occupants and site operators, they make a difference in terms of their behavior because they can interact with equipment. It's not only their load that their body imposes, but also their behavior in vis-a-vis specific pieces of equipment that it can impact the consumption of various energy systems. The ESCO contract affects system performance in terms of what the ESCO's duties are and what obligations they have and responsibilities. In this case, JCI has a very sizable maintenance contract, and they have a fair amount of operational responsibility for providing maintenance. Then there's the degree of internal staff. And correct me if I'm wrong about this, Jeff, but hasn't the legislature managed to radically decrease your staffing level for operation and maintenance over the last 5-10 years?
No, it hasn't decreased, but it doesn't increase.
Okay, so what you're saying is your responsibilities go up, but your staff doesn't.
Correct.
So that's more the logic. It's not that you've lost staff, it's just that you get a lot more things to maintain and operate, and you don't get more staff to do it.
Right. Or money.
Or money. So how many people there are able to work the two jobs at once like you do?
A lot of people.
Yeah, no, I know this.
Let me tell you, for love.
Yeah.
Work overtime.
Well, I know it. I mean unfortunately, I'm seeing that more and more in the public sector generally. Is that either there's a vacancy because somebody retires, but they don't hire anybody new, or they add new facilities, but they don't add any new staff or budget, and they just say, well, your existing staff or budget, they'll take care of that. But all these things can affect system performance, because if you're always running to chase issues, then the ability to sit back and come up with a strategic plan and optimize becomes, there's less resources available for it. But also, agency finance staff, your interaction with the utility companies affects your system performance. We talked about this a little before. Things like power quality, things like having your interconnect agreements approved in a timely manner, that can affect how much savings you get out of your PV systems in a particular time. And then there's laws and regulations. as it relates to how you operate your equipment. I guess, for example, would be when you cited your PD systems, you had to meet, I'm assuming, FAA requirements, so you didn't interfere with aviation function, correct?
The glint and glare study, yes.
Yeah, exactly. So let's go to slide 99. So, how do you create a high-performance culture? Well, there's nothing so stable as a habit. And whenever I learn how to do something, I like to keep doing it that way. So when you put in a whole new bunch of equipment, if it's really new equipment and it requires me to change my habit of operation and the way I did things before, sometimes that's a stretch. And it may require, that new equipment may require new habits of operation and new strategies. And especially as people become familiar with the capabilities of an EMS system, that may be a learning curve that you have to go up as you adapt the old habits of operation to the new capabilities of your new equipment and your new system. It's also important when the ESCO is doing agency staff training to help them understand all the benefits and potentials of the new controls and equipment. And ultimately, you're forming what I call a public-private partnership, where the ESCO is your partner, helping support you in achieving your mutual goals of saving energy and having the best operating facility that you can. But it's also important to have sort of a proactive maintenance with regard to the energy management system. And the thing about it is, especially you go into this chiller optimization that's going to be possible once OST is all looped in and the chiller piping project is completed, is that mutual learning, through the shared experience of implementing this optimization can bring about, better than average savings performance, where you can actually exceed your savings targets over time. So let's go to slide 100. So why is training so important? Well, this is based on some studies done in the industry. About 30 to 50% of maintenance failures are due to lack of maintenance knowledge by staff. In other words, they're being faced with equipment which maybe they've never gotten adequate training on how to maintain or operate that particular equipment. Or, you've had a turnover in staff and the new person is still getting up the learning curve and, does not have all the information that they need yet, but eventually they'll get it. Or sometimes, even if you know what to do, and you have the knowledge, maybe you just don't have enough time or budget, and you don't follow the best maintenance practice, and so there can be a failure with respect to some particular piece of equipment. Filter changing is great example of that. I've seen many cases where filters were supposed to be being changed, and that was low on the totem pole of their maintenance path, so they didn't get changed. It created issues. Sometimes maintenance staff just lack fundamental knowledge of what the best practices are because they've never had a high level of O&M training because there wasn't a budget for it. And something that every agency should be worried about is that as their staff gets older, the baby boomer generation, of which I'm a member, starts retiring, there's going to be a loss 40 to 70% of existing maintenance personnel. And they won't necessarily be that easy to replace. Go to the next slide. So these are some ways that the ESCO can support savings performance of the project. They help operators understand the level of set point flexibility that is reasonable with equipment. Because there's always some deadband. You might have a target, but certain changes are not as dramatic on their impact and savings than other changes. And if you understand the implications of, change 1 is not the same as change 2 with a set point, that can be helpful. If you show them how to interpret trend data so they understand, what the consequences of a particular trend and over time, what it means, and understanding their role in the overall performance optimization and how they can be supported by the ESCO and how you can work together in sort of a team formation. And then looking at the difference between, I'll call it short-term solutions and long-term solutions. And a lot of times when we're under pressure, we try to do the thing that will solve the problem, the short-term problem, in the quickest, easiest way. But sometimes it creates long-term damage. Excuse me. So weighing the short-term benefit versus the long-term and making an appropriate decision can also be an area where the ESCO input can be very helpful. Go to 102. So, believe it or not, this is the last slide. And this is just a sort of a summary, excuse me, of what makes a successful M&V on a project. Well, you need a timely method of tracking savings. It's got to be cost effective, it's got to be clearly defined, and it's got to be reasonably accurate. And that's, fairly straightforward. Excuse me. But those are just some of the basics. Believe it or not, I'm sort of open for any questions you might have because we're down to the last few minutes here and you've actually made it through the second webinar.
What happened? Did I lose the audio?
No, we're all very quiet waiting for a question.
All right, I'll ask a question of myself. So my understanding is that chilled water valves and actuators are new, and they're new VFDs for the renovated central plant because you found that a lot of the chilled water control valves were non-functional. That's correct, right?
Yes, just a little added information is that most of the control valves were three-way valves. So converting over to a two-way valve allowed us to convert to a variable pumping schematic for those energy savings opportunity.
Yep.
And then on top of that, it was pneumatic actuation for a large percentage of the valves. And so we went with full electrical or electronic actuation and full DDC on the fan systems.
And it was also true that a lot of the air handler VFDs were inoperable or in hand or bypass mode as well, right?
Correct, just really from age and deferred maintenance.
Yeah, so most of the AVs were operating at full speed most of the time.
Or bypass, yes.
Yeah. So now, not only do you have a better control system, but you have a lot of the ancillary, I'll call it, control components in the field have been upgraded and replaced so that they can actually function in response to control signals.
That's true. Primarily what got replaced at H&L was a monitoring and a stop-start of fan systems to full DDC control, temperature control of the units.
Mm-hmm. And also I understand that you're working on providing enterprise web data management system or an energy information system. And it's, I think from comments you made earlier in the webinar, you're still in the developmental stage in terms of fully implementing it, but you're in the process of getting it fully implemented with the dashboards, etc.
That's correct.
Do you have a time frame for, I'll call it, full implementation of the enterprise-wide data management system, the EIS?
Soon.
Okay.
We're still having weekly calls on that, Dave, so it's work in progress.
Okay.
It hasn't been my highest priority, so I'm clearing my plate of some other things to give attention to it.
And will that include facility performance indexing?
Yes, that will be a component of it.
Okay, great. And then, last but not least, commissioning. Are you waiting to do the more full-scale commissioning on the integrated chiller plant, obviously, until you complete the OST piping? But in terms of the commissioning for, I'll call it, stuff that's there now, how many months out before I'll see commissioning reports? Are we 1 month, 2 months, 3 months away?
I'll say
Documentation.
yes. I mean, it really is compiling that, Dave, and we're looking at 2 to 3 months out.
Okay. Well, that's helpful just for planning because it's still one of my tasks for Jeff, and I knew that it was a few months in the future, but I just thought I would check. Well, thanks everyone for your attention, and thanks for JCI hosting, for DBET for funding it. Appreciate it.
Okay, so I'm going to stop recording at this time.
Yeah, thanks, Larry, for doing that.
Not a problem.
Benton, if you guys want to listen to the first one, it's on that link there. You can listen to the first one. It's recorded.
Yeah, it's not a problem. I was going through it while earlier, so I did have one question. Larry, wouldn't it be prudent that we're going to be doing our M&Vs based on the calculations and the methodology you use to do the base calculations?
Yes, the measurement and verification methodology is actually spelled out in Schedule D of the contract.
Right.
So if I'm following you right, Benton, I think we have been doing that, and that's the process that we're following.
Right. I just wanted to confirm that.
Okay.
Schedule D.
David, yes.
Yeah, I'm here.
Schedule D is in David, I'm sorry.
Oh, yeah, okay.